Hello everybody, this is Han, and today I'm gonna present about clock synchronization in 3D ICs. Today's agenda will go through the background of 3D integration, the advantages, applications, and challenges, and then we'll go deeper into synchronization in 3D ICs, which would focus mostly on two approaches. One is by using clock distribution topologies, and the other is to have die-to-die synchronization with delay lock loops. So what is 3D ICs? 3D ICs are basically three-dimension integrated circuits that works by having multiple active silicon layers stacking on top of each other. This technology enables a lot of performance potential in reducing 2D area of the chip, reducing the footprint of the chip, and by that having higher logic density, higher packing density, and with higher packing density, global interconnects would not be necessary anymore. And the amount of metal used in interconnect manufacturing and also would be reduced. And by reducing these interconnects, we also have lower power consumptions. 3D integration, aside from its performance potential, also enables us to have heterogeneous systems, in which I would talk more in the application section. Now, here are some of the applications that stems from 3D integration technique. First is hybrid memory cube. So it is basically stacking memory dies on top of logic dies, so that we would have wide bus widths between logic layer and memory layer. This was specifically what the bus grade between these two vertically integrated layers. It's much wider than having the bus run on one side of the push. So some of the examples of 3D ICs are hybrid memory logic cube, which is basically stacking logic layers on memory layers on top of logic layers, and enable a wide bus width between the two layers, because the constraint now for the bus width is just the area of the overlap area between the two chips, the two dies, instead of having the bus width constrained by the length of the dies. This will enable near memory computing, because we're bringing the memory much closer to the logic layers, and would therefore reduce the effect of the memory wall bottleneck on data intensive applications. Another example is hybrid memory hierarchies, which combines multiple memory technologies such as SRAM, STT-RAM, RARAM, phase change memory on different dies stacking on top of each other, and that will optimize for various parameters that each memory technology is strong at, such as power, density, cost, etc. Then the third application I'm going to introduce is 3D stacked arithmetics unit. And 3D stacked multi-core processors, which are basically multiple logic layers stacking on top of each other. And these kind of architecture has already been used in the industry via the manufacturing of the Intel Xeon Phi, which was out in 2016, and the NVIDIA's Pascal GPU architecture with 3D stacked RAM. All right, and next up, we're going to talk about the challenges that 3D ICs might face when designing. First is the thermal issues, because we have such a high density of active device near each other. The heat sinking for these devices should be optimized in order for the heat system not to overheat. The second one is the high cost of manufacturing these 3D ICs, as the process of manufacturing these would differ a lot from 2D ICs, because it has to because for 3D ICs, manufacturers have to do more alignment with vertical stack chips, and also manufacturing the true silicon vias, which are the interconnect between layers. Since synchronization in 3D ICs account for a substantial proportion of the power consumption of the overall chip, so today we're gonna go deeper in it and try to optimize this. All right, from this point, we're moving on to synchronization in 3D ICs. There are multiple approaches to tackle this problem in 3D ICs. And since we're using true silicon vias, which are metal connects between different layers that are vertically integrated to each other, we have to model the electrical characteristics of these vias for delay and power simulations. The synchronization, since so in the goal of synchronization is to ensure that the delay between the clock source and the leaves has to be similar between different leaves, or may I say different logic cluster on their IC, no matter where they are. And to minimize this, we should look at the clock distribution topologies on how these clock signals may be delivered to different logic cluster on the IC. And this is different from 2D IC, since these clusters are now reside on different dies, and there might be different delays when going from one die to another. Lastly, we'll look at the approach of using die-to-die synchronization, so we do not have to care too much about the clock distribution topologies between the dies. This will give us more flexibilities on designing our topologies on each dies. Okay, so now we're going deeper into the distribution topology approach. So first of all, how did they do it in 2D ICs? In 2D ICs, we have tree structures of X tree and H tree and buffer tree, which I would be showing you in the next slides. And these kind of trees are usually symmetrical, and the symmetry of them usually helps to minimize the difference in signal arrival time at the leaves. And aside of the trees, we would have mesh and rings interconnects, and these mesh and rings usually reduce the interconnect resistance when compared to tree structures. And it also decreases the clock skew because clock skew is usually proportional to the interconnect lengths. But with these mesh and rings topologies, the compatibility is limited, not based on the placement of the logic clusters. So the general rule of thumb is that the more global the synchronization is, the more power it consumes. So that's the design patterns we have to look at. Here are some pictures demonstrating what H tree is, X tree is, and grid is. Grid and from trunk to mesh tree is. So how do 3D clock distribution differs? So because as I've said before, clock signal propagates between layers, and because of the via's presence between their layers, they might have different impedance, so resulting in different delays going from one layer to another. And our mission is to make sure the clock signal is delivered in a similar latency to different leaves, no matter which plane it is. So now I'm gonna introduce some clock distribution topologies that were researched and experimented on in a paper by Dr. Savidis, Pavlidis, and Dr. Friedman. First, we're going to look at is the H3 topology. Their experiments mostly conducted on a 3-layer 3D stacked IC, which has similar logic on each layer, and the clock source is generated in the middle of the second plane, which will be propagated onto the first and the third plane. And our mission is to try to minimize the delay at each leaves on third plane and minimize the difference in delay between each leaf on third plane and first plane. So in this all H3 topology clock distribution, only one cluster of vias is needed to connect the 3 planes, which is demonstrated here on the dotted line. It connects the clock source in the middle of the third and second plane to the middle of the third plane and middle of first plane, which will be distributed onto the H3 topologies on third and first plane. The reason why the third plane and first plane topologies is rotated 90 degrees from the second plane is to avoid inductive coupling between parallels interconnects on the two dies, on each pair of dies. All right. The second one we're going to look at is the local ring H3 and then local ring. So the third and first plane will have local ring topologies, while the second one has the H3 topology. And with this configuration, the vias would be placed such that each local ring would be connected to one leaf on the H3 on the second ring, on the second plane. As you can see here, there are a lot of clusters of vias, each connected one global ring to a leaf. And lastly, we will talk about the global ring, H3 global ring topologies, where layer 1 and layer 3 implemented a global ring topology, and the vias placed in this configuration, such that each periodic segment of the global ring is connected to a subtree in the H3 on the second plane. So after looking at all the three topologies, we have to decide on which one to use and what will optimize on what. So for the H3 symmetry, the H3 symmetry helps with the latency difference at the leaves. As you can see, it's a very symmetrical topology which guarantees this. But in exchange for that, the H3 topologies we see at the beginning has a very high power consumption because it has a long interconnect with even more. And if we use the tapered H3 topology, then it would create more power consumption at a large interconnect um, on nearer to the clock source. Um, with the global ring, uh, it compensates for the VR's latency, but and also its lower power. And with the local ring usage, we encounter a higher clock skew, but it consumes the least power because it eliminates long clock paths on the plane. So based on the three topologies observed, we can see that there are some trends to be recognized, which is the power consumption of a topology is inversely proportional to the number of TSV. So the number on the local ring topology, we can see that there was a lot of VS cluster needs to be placed for each of the local ring. And when experimented, data has shown that the power consumption of this topology to be the least among the three. And another trend is that the timing skew is also proportional to the number of TSVs. So the the on the local ring, also on the local ring topology, we observe the highest clock skew among the three when it has the most number of the highest number of TSVs. So in conclusion, the choice to use each topology depends on the constraint of each design, whether you want to optimize for power consumption or whether you want to optimize for timing skew between clock source and leaves. Okay, so now we're going to move on to the last approach, which is die-to-die synchronization with delay lock loops. This was based on a paper by Chiwei K and a lot and other people. They used delay lock loops with dual locking mechanism to do synchronization between die and die, and this will let us have the flexibility of not having a fixed topologies following their one of the three topologies introduced in the last section, but rather any topology we want on each plane and have the clock signal on both planes synchronized to each other. So first of all, what is a delay lock loops? A background on delay lock loop is that it's similar to a phase lock loop, but instead of having the voltage control oscillator, we have a voltage control delay line over here, which is basically constructed by a series of buffers whose delay can be determined by a control voltage calculated from this part, which is similar to the first part of the phase lock loop. And this delay lock loop is used in such a way that this delay line will create will be a delay such that the out signal here is slower than the reference signal in by a multiple of the period. So it aligns the phase of these two signal out and reference. So the conventional way of using delay lock loops synchronization between dies is to have an input clock in the delay line, and then the input clock in. This is the delay lock loop, and then after it's synchronized, it will be put on onto the forward transmission line to a remote clock on a different die. So the clock signal on the different die is over here, and the clock signal that will be used for the source plane, source die will be here, and eventually from the remote, the receiver die, the clock signal will come back through this feedback clock and be aligned again with the input clock. But this would work perfectly fine if the feedback transmission line and the forward transmission line has the same delay. Or if so this only works on the premise of that. Otherwise, if the delay caused by the forward transmission line and the feedback transmission line is not equal to each other, there would be clock skew occurred. So this is dependent on the delay caused by the transmission line. So in Chi-Wei K paper, he presented the dual locking architecture, which uses two delay lock loops and some tri-state buffer over here. And note that on the second die, the receiver die, the delay lock loop has a two-phase digitally controlled delay line here. Using this setup, with this setup, it is independent from the latency caused by the TSV. It is independent from the delay caused by the transmission line between these two, die 1 and die 2. And thus, because of that, it has higher tolerance against process and environment variation. So how these this dual locking mechanism work is that it has two lines, the feedback line and their forward line. And these two lines are used in two steps. And I'm gonna go through these two steps now. So for step 1, the feedback line is used here in green. Start from this signal 1 here, goes through this tri-state buffer through wire 2. And here the net name is renamed as feedback signal into the phase detector to be aligned with die 1 signal, which is the clock source. Note that the feedback signal here is lags behind the signal 1 here by exactly the synchronization path delay caused by this wire 2, which from now on we will use delta to depict it. On this waveform, we can see that after the delay lock loop 1 has come to action and aligned the two signal, die 1 signal here and feedback signal here is aligned with each other. And since feedback lags behind signal 1 by a delta amount, we can see here signal 1 is ahead of feedback and die 1 by a delta amount right here. And to continue, step 2, on step 2, we are going to use the forward line to align the signals. And when the forward line is used, the delay lock loop 2 will come into action. It will try to align the forward signal and the out signal here to be in the same phase. Note that the signal that is finally get fed onto the get fed out on the die2 clock distribution topology is actually die2 here, and it's acted as a clock source for die2. So here on step 2, we align the out signal here and the forward signal here, as you can see. So after we align a forward signal and out signal, we will have the and from step 2 we know that the forward signal lags behind the die1 signal by a delta amount, because it has to account for the delay caused by this wire 2 interconnect. As you can see on this waveform, forward lags behind forward lags behind die1 by 1 delta. And from step 1, delta 1 is ahead of die1 by delta. So in conclusion, from 1 and 2, we know that signal out lags behind die1 by exactly 2 delta. So signal out here lags behind die1 by exactly 2 delta. If we look closer into the two-phase delay lock loop, signal 1 and signal and signal out, which is 2 delta apart, we can cut the delay line into 2 identical separate parts, and each will resemble 1 delta. And therefore, in order to have a signal die2 that is exactly aligned with die1, we have to have it lags behind. And we have to have it we have to have it lag behind a signal 1 by exactly delta, and ahead of signal out by exactly 1 delta. As you can see here, they are aligned. And this is just a result from the paper of using the architecture proposed to align the 2 clock source on die1 and die2 with 200 megahertz. They aligns more better than at 600 megahertz. So yeah, that's all. So we have synchronization in 3D ICs is a challenging task, and there are more variables to consider than synchronization in 2D. And via this presentation, 2 main approaches were introduced, shows great potential to be used in 3D synchronization as a framework, but there are still challenges to overcome. For example, for the delay lock loop approach, we were only synchronizing between 2 dies at a time. So more research has to be done in order to synchronize more than 2 dies at the same time. And also for the clock distribution network approach, we didn't have the flexibility to have non-symmetrical design between die 1 and die 3. Um, whereas we in some design constraint that could not happen, so we need more we will be needing more research into uh, figuring out how to do how to depend on clock topologies, clock distribution topologies to do synchronization without without having them to be exactly symmetrical. Um, that is all. Thank you for listening to my presentation.